In this lecture, we'll discuss about design and verification of traffic light controller. We'll do both design and verification with Verilog. Okay. So to do this project, it's like a mini project. Okay, Verilog based mini project. To do this project, we need state diagram because in traffic light controller there are states like red, green, yellow. Those are states. We need to maintain particular state, and after some time we have to move to another state. It means traffic light controller has to move to another state. So in general, in the traffic light controller, the electronic circuit is counter. So we are maintaining in particular state, or we are being in the particular state for some time, particular time, by counting clock pulses. So when I explained about counter in digital, I told counting means counting clock pulses. So we measure the time by counting clock pulses. That time I told traffic light controller example. Okay. So suppose now if I want to, or if the traffic light controller want to be in the red state for 5 seconds. Okay. So if each clock edge time taking 1 second, so we have to count 5 clock edges to be in the that red state in the 5 seconds. Okay, so we count the clock pulses to measure the time. Okay, so this is the actual functionality. So now this is the state diagram. There are 3 states: red, green, yellow. So initially this red state is like a reset state. Initially we will be in the reset state, or when count is 0 we will be in the reset state. So here just an example I am taking. When count goes to 5, initially count is 0. From 0 to 5, when it is go to 5, I have to go to from red to green state. This is my assumption. Okay, you can take any time. Okay, right. When time reached to 10, I have to go from green to yellow. This 10 count means from starting to here. From starting to here. Okay, from starting to 10 means. And if count reach 15, from starting to 15, it has to go to yellow to red. Again it will go again after count reaching from 15 to another 5 means 20. It means count after 5 again it will go to green. So it will happen until the counter is traffic light controller is on. It will happen like this. Okay, so this same functionality, these values I assumed. Why I take in second state? Generally in the traffic light controller, if we observe after red we will get green, then we will get like a yellow indication. It indicates it is going to get a red state. Okay, so accordingly I take it. Okay, right. So now we'll see the design code, then we'll do the verification code also, and we'll run the code and we'll analyze the simulated output. Okay, so module, and at the ending it will end with end module, you know. So I did this coding with behavioral style. Okay, so TLC is my module name, and what are the inputs and outputs? Clock. So counter means it's a sequential circuit, synchronous sequential circuit. It work with the clock edges, so we need clock and reset. You know, sometimes we need a reset option also to go to initial state, red state. Okay, right. So we need clock and reset, and state and count. 2 more variables, state and count. State, what is telling which state we are in. That state is nothing but whether we are in red or yellow or green. And count, to measure the count value we need some variable, na? And to say the state also we need some variable. That's why we taken. So the state and count are output variables. Okay, right. So here clock and reset are input, state and count are outputs. Initially I initialized my count is 0. Okay, from 0 it will start counting. Okay, so here see, you can see output ports. And why I wrote reg here, because in this procedural block at the statement left hand side you can see count there at left hand side. Okay, and here where is state, see here state also at left hand side. Okay, alright, that's why we write reg. Why this state is 2-bit size? You know total how many states? 3 states. Like in memory, if there are 3 locations, how many addresses you need? 3 addresses. To give 3 addresses you just need 2-bit address, right? Like that here for 3 states we just need size 2-bit. So to represent 3 states you just need 2-bit right size. Okay, right. Now why count value is size is 4? So here what is the maximum count I taken in the state diagram? 15. That 15 is the decimal. If you represent in binary, minimum how many bits binary you need? 4 bits are enough, na? So that count size you have to take based on the maximum count value. When you convert that maximum count decimal count into binary, how many bits minimum you need, that much size you have to keep here. And this states size based on the number of states. Okay, and this state encoding I am doing in binary, not in 1 hot. If you are doing in 1 hot, it may need more bits. So I am doing a straight binary. So this red state I am assuming as 0 0 0 1 1 1. You know, with 2 bits you can get 0 0 0 1 1 0 1 1, 4 possibilities. You no need to write in sequence 0 0 0 1, either 1 1 or 1 0. Anyone you can use. I taken 1 1. I neglected 1 0. Okay, out of 4 you need 3. Any 3 you can take. Okay, now here you can see parameter. Now I will tell what is the parameter. So parameter syntax is parameter keyword, after keyword there is a space, and this is called parameter name. So here you can see parameter name in capital letter. It is not compulsory. To make them highlight parameter names we use it to write in capital letters. And this is called parameter value. After parameter name you have to keep equal to, and you have to write the parameter value. After parameter value you have to keep semicolon. This is the syntax of parameter. I will tell the purpose of parameter. Now I told the syntax how to write. So this value you can write in decimal or any base. Okay, suppose here this 0 I wrote, this is nothing but without base, this is nothing but 0 decimal. It will take as 4-bit binary, because you mentioned this size na, so it will take as 4-bit binary. Like that also these numbers we can write. Here clearly we are writing with base and size. Okay, right. So now what is the necessity of parameter, we'll see. Suppose if I don't use parameter, here everywhere what I have to write here, I have to write values. Okay, now because of this parameter, wherever in the code this parameter names come, in that parameter names this value will become substitute. Here it means state equal to what will come? Red means 2 tick 0 0. This will become 0 0. So if you write that, that is called hard coded values. In coding we generally avoid coding hard coded values. We use like this parameters. Okay, so parameter purpose is reusability. Parameter purpose is reusability. Suppose if I replace some other variable here, in that variable this value will become replaced. So in some other lectures I will show you how this parameter is reusable. Okay, but in this code mainly we will discuss about traffic light controller. Okay, right. Now this is called parameter declaration. This is port declaration. Which one? This. Okay, right. Now I need a procedural block. To code the functionality I need always procedural block, that also with sensitivity list. I want to make it as a synchronous reset, that's why I have not included reset here. And I want to make it as a pause to clock edge circuit, that's why I take in pause to clock. Okay, so there are multiple statements I am going to write, so I used begin. So for this begin, this is the end. Okay, now, so in the state diagram what I shown initially, I told you red state is a reset state. So if I apply reset, I should be in the red state. So this is active high reset. So if I apply reset in red state means reset equal to 1, it means, so it is active high reset. So this is the statement. So before the statement begin I wrote, after the statement I wrote end. Even you don't write, no problem, but you do like this, it will become habit as a good programming practice. Okay, right. Else it means when you release it reset, when you release it reset. So here we have to write non-blocking. I will keep non-blocking, just a minute. Okay, and here also. Okay, here also. Okay, I am saving. Now else means when I release it reset, what should happen? Count should start. Okay, so where, from which state it will start? It will start from red state. So when I am in red state, when count started, if the count reached to 5, so how count will happen? This count is initial, previously we given 0 na in above, so this how it will become? So this is 0 initial, 0 plus 1, what will happen? 1. Now this count will become 1, 1 plus 1, like that it will go on increment until 5. When it reached, we mentioned na 5, so when this count reached to 5, we will go to which state? Green state. We will go to green state. Okay, right. So here you can see I used begin here, I used end here. For this begin, this begin, this is the end, because this, in this whole code there are two parts. This is the reset part, this is the non-reset part. This whole non-reset part I kept in one begin end block. In this begin end block, these all actions will happen. Okay, so here before this statement I used begin, after this so here, so these all statements I kept in this begin end. So for this begin, this is the end, and this statement before I kept begin and after I kept end. So this begin, this end, you can see this begin, this end, this begin, this end, this begin, this end, this begin, this end, this end is this begin, and this begin, this end. Okay, right. This else is applicable to this one. So when count reached to 5, I should go to green state. Now what is the state? Green. When I am in green state, if count reached to 10, from the starting, from this initial 0 to 10, it means after this 5 again another more 5. Okay, reach to 10, where should I go? Yellow state. So now the present state is yellow. When count reaches to 15, I should go to red, again starting. From the red it will count again another 5, it will go to green. Like that loop will continue until that traffic light controller is on. Why I take in 5, 10, 15? As example, you can take anything. Okay, so this is the design code. Now we'll go to Testbench code. But when you take a count, based on that count you have to take the size of this variable count. Okay, now Testbench code. So in this Testbench I included, this is also start with module and end module. Okay, so now range and wire declaration, you know, Okay, and this is the instantiation. In previous lectures I explained about all these things. Okay, now here I have to generate the clock, I have to generate the reset, and in the clock I used it forever, so I have to use finish. So here there are no inputs except clock and reset, so you no need to generate any input here, no input generation. Okay, and I am not asking you transcript also, just I will observe the waveform, because that will be the better analyzation for this project than transcript. Okay, so initial for this clock I taken one initial block, for the reset I taken one initial block. Okay, now I will do one thing, just a minute. I will keep this finish in separate block. I will end here. Now again one more initial, begin, later I will keep end. Okay, so now we can remove this one. So here this is one initial block, this is begin, and this is the end, and this is the forever block in the initial, furthest to forever, this is the begin, this is the end. So here we no need this begin and only one statement, but I wrote. Okay, and this initial, second initial block, this is the begin, and this is the end. This is all for reset. Okay, and in this I used, this is another procedural block for $finish, so initial and begin end. Okay, now I saved. So I taken as example 500 finishing time. Okay, so initial clock position I taken 0 and time period as 10. It means for every 5 time minutes it will clock will invert. Okay, because of this forever. Okay, now how I coded reset, see, initially I applied clock, applied reset, but after it indicates what it indicates, at the rate of passage clock, when we will get positive clock at 5 picoseconds or 5 nanoseconds, whatever the time, simulated time. Okay, it means at 0 time minutes you applied the reset, at 5 reset will be become 0. You are telling na, at the rate of passage clock means we will get first passage clock, because this is 0 initially, after 5 we will get first positive clockage, so at that time only you are telling to make it reset. So here this at the rate indicates delay based control. Suppose instead of this I can do like this, #5. It also indicate after 5 time minutes you want to make it reset. Either you can write #5 semicolon, then reset equal to 0 semicolon. This is called delay based control. If you write like this, if you write at the rate like this, this is called event based control. Anything is okay. Okay, suppose if you write here before this at the rate always, this circuit will become reset, will release reset, it will become 0, reset become 0 at every positive clock edge if you do always it. Okay, I don't want to make this circuit 0, reset 0 at every positive clock edge, so I just want to release the reset at first clock edge. That's why I wrote like this. After 150 time minutes I want to make the reset, and again 200, after 200 I want to release. Why I coded like this? This is our wish, you can do anyway, na? This clock also, this also you can do anyway, this even finish time also. Okay, right. So now you can see the run file. Okay, now I will copy this path and I will execute the code. Okay, so I will go to that. So TLC, I will take this Control C, I will simulate in model sim. So this is like a mini project, but even it is a mini project, you can get the concept, na? Initially we should do only mini projects. Now you can understand, because of this project you can understand what is a counter functionality exactly, and traffic light controller project also we can understand. Okay, so click on this, zoom it. Okay, so now this is this side, you move this side. Okay, now initially my clock position 0 I given, after 5 I told it has to invert, for every 5 seconds it has to invert. Okay, initially at 0 I given reset, but at 5 I released reset. Again where I applied reset, I given I think 150, na? See here, 155. It means 155, how it is counting? From this 5, from this 5 to until that point, total 150, from starting to 155, like that. Again see here, I release it, it will become, okay, how it is becoming 355, we'll see. Where is the code? See here the time durations, this is 5, this is 155, this is 200, 355. Okay, right, 355. Okay, so now reset also came as we told, as we coded. Now see here, this state value 2-bit, see here this count value is 4-bit as we given. Okay, so here first clock is started, so before this output is input is this state is unknown. Okay, because here only first clock edge is starting, na? Because the circuit is work with positive edges. Okay, so from here to count to clock pulses, so initially what is the state? We are 0 0. So 0 0 means what is the state we given in the code? We have to look into parameter. 0 0 means which state? 0 0 means red state, 1 1 means green state, 0 1 means yellow state. Remember that. Okay, so 0 0 means initially we are in the red state. Okay, so it means see count 0, when count 0, all zeros, there I given 0 decimal, so that will be converted into 4-bit binary. When all count is 0, we are in red state. So now count started, count is 1, count is 2, count is 3, count is 4. Okay, so after 4 count 5 reaching, so we came to so count is 5. So here after count 5 we reach to this state. What is 1 1? Green state. You can see this bus change here. Okay, so this every count happen with respect to clock edge, positive edge. So from here to here to count this, how much time it taken? 10. From here to here 20, 30, 40, 50. Okay, so at the next stage it is reaching to next state. Okay, so here we measured how much time to reach this state. How much time we measured from here to 10, 20, 30, 40, 50, 60. So when it means 60 means after each count is taking, how much time each count taking? So count started 0 0, so this is 0 0, so this is 1. 0 to 1 count, how much time it taking? 10 it is taking, 10 picoseconds it is taking. So we are measuring each count with clock pulses. So we are counting clock pulses here, so that we are measuring time. So we measure the time by counting the clock pulses. This is the purpose of a counter. Okay, so after count 5, this is 5 only na count, After count 5, see, it went to next state. Again from here we have to start count. Okay, see here, what is the count? This is, we reached to count 10. Immediately after 10, so you have to see this count values. See, I told initial count is 0. See, when I reach to 5, what is the next state? Green. Again when I reach to 10, what is the next state? Yellow. Okay, then when I reached, see here, okay, I reached to 14, but 15 not came because I did reset. You know, if I don't do reset, I may get 15. I may go to again red state. But here I applied reset. Even I apply reset, I have to go to red state. Even after this 15 count also, I have to go to red state. But here this red state came because of reset, not because we reached 15. If I don't apply reset, I may reach to 15. In that case also, I may go to red state. Okay, right. So to show the reset operation also, I did like this. Okay, because I applied reset at this time. Now somewhere I released reset na, again it has to work as per the functionality. So I released reset. So where it is before? Red state. 0 0 means red state. Now that 15 you are getting. So this is 14. Now you are getting 15. Okay, so now again count will start. After 15 it will go to 0 na. 1 2 3 4 5. Again after 5, where it has to go? To green state. So it will do until you on this traffic light control. It will work like this. Okay, right. So we did design and verification of this traffic light controller mini project by using Verilog, and we ran the code and we analyzed the output very perfectly. Okay, right.